All right, so we are recording. I'm going to share the screen. All right, so we are recording. All right, so currently I believe we're on week 10. Double check on that. That means that we have our next exam in 2 weeks on week 12. All right, it's going to be a written exam. Also, the practical exam will likely be that Thursday, right? So we've already done a quiz and you kind of saw how it works, but you're also going to be using more scripts, right? So we're going to use everything. As I've said, I will hide a quote from a movie, so you can assume that I'm going to follow the correct encryption protocol. So that means I will have a key that will be encrypted with RSA, most likely. And then I will have I'll use that key, that secret key, to encrypt the message with something like AES. So the scripts that you will use are that RSA from scratch code that I showed you how to crack RSA. You know what that's for. Most of the other scripts will probably be from the PyCryptodome library. And I could throw in like the toy as well, the toy RSA. Does that make sense? Or maybe some OpenSSL. Can have a cheat sheet, of all the commands, all those, all the scripts and what they're for. You can have the scripts available, obviously, on your computer already, right? And then we'll start the demos this week for the homework. Remember the last homework that we did, where you're working with your partner and you're sending them a message and you're exchanging the two problems we did. So you have to demo. So I'll sit with you guys. We may not get to everyone on Thursday, so that'll probably take this Thursday and the following Thursday, but you can work on the lab while I'm doing it. So there will be some students that will finish first, so I'll go sit with them, and then the rest can work on it. Okay? Shouldn't take more than 10 minutes if you know what you're doing, if you practice, just really quick, and you can have everything ready. The only thing I do is usually I ask you to open the message and I change it just to make sure that you are encrypting what I ask you. Got it? Any questions about any of that? So start demos this Thursday and next Thursday. That's weeks 10 and 11. And then week 12, written exam and the practical scavenger hunt is usually what I call it, because you're like hunting for something, a message. Questions on any of that? No? All right, great. So today we have several things to cover. One of them is Diffie-Hellman. So we're going to go over the Diffie-Hellman algorithm. So I'll give you a little bit of a background on it. It's important historically. So I kind of want to, pay credit to that. So we'll talk a little bit about that. Then I'll go over the algorithm. We'll do similar to the toy RSA. I'm not going to get into like the weeds of it. We're just going to do a toy RSA. It uses modulo, mod operations. So you already know how to do that. It's just a different algorithm, and it's kind of interesting. It has some weaknesses though. So obviously you can see how RSA has become more popular. One of the themes this week also for the lab will be performance. And we'll see that Diffie-Hellman might be way slower than RSA. So you know that the choice you want to, remember, you want to get to that Netflix movie in a minute, not 30 minutes from now, right? So, but at the same time, it also needs to be encrypted. So we'll go over like the notes, and then I'll go over an example, okay? And then that will be we'll do some examples of OpenSSL also today. Just kind of RSA, Diffie-Hellman, looking at the information. If time permits, and then I'll start getting into digital certificates. All right, so the next sequence is digital certificates and certificate authorities. So there will be several labs for that. You've already done one digital signature, so you should understand how that works, and we're just going to continue to get on that. And then I do have some slides also that I do want to touch on. They're basically just things that I've said already, but they just summarize some ideas, and I have some graphics there. So we'll go over those. They should be, we are basically PyCrypto. We're done with that. We're kind of here. This is the module. The lab certainly is this one for this week. And then I do remind me to talk about the project this week, given that we are in week 10. The last week is week 16. So that means you have 6 weeks left until the semester's over, right? So you have to start working on the term project. The project is only worth 10% of your grade, so I never make it like a big project, but we'll talk about some ideas of what you can do. And then, yeah, we only have Diffie-Hellman and summarize what SSL is, but you already know what SSL is. We'll talk about what the TLS protocol is, which is just an extension of SSL. And we have a few things left, like more application things, like Bitcoin and crypto, blockchain. Also, we do elliptic curves, right? So we do have a few, and then a little bit of like the quantum computing thing, how to break RSA with a quantum computer. That's just really a Python library simulating a quantum computer. So that's basically the semester. There are applications like how to use it for malware, for denial of service attack, defense, and various other things. So yeah, we're getting more into applications versus the algorithms themselves. But I do want to cover Diffie-Hellman today a little bit. So we'll get into that. All right. Any questions before I begin? All right, great. So hopefully you made a note of all the dates, everything we got coming. All right, so I'm going to go ahead and share the screen here. And the algorithm is simple, actually. So, oops. So the algorithm is simple, and we'll do an example. All right, and here we are. Change color to red. All right, so today's topic, Diffie-Hellman. This is similar to asymmetric encryption, right? So it relates to key exchange, right? So the problem, so this, first I'll state the name of this. So it is Diffie-Hellman. So what does that mean? So it's two people. So it's two professors, actually. I forget what school it is. But in 1977 or 76, it might have been 76. Let's say 76. All right, so in 1976, they published a paper, and I think it was called like The Future of Cryptography or something like that. Very bold statement, but it's actually a really important paper, right? So up until then, it was just symmetric encryption, right? It was all what you know, AES, DES, block cipher, the problem you had all semester of how do you exchange the key. That was the state of things. People had to meet in coffee shops and exchange in a secret envelope the key and things like that, right? So you needed a way to exchange keys. So then these two professors, Diffie and Hellman in 1976, they published this paper and they proposed this idea of how to arrive at a secret key without without having to meet offline in a coffee shop somewhere. So their algorithm was interesting, like revolutionary. The idea, they actually coined the term public and private key, okay? But it had weaknesses. So it's slow. It only works for like a set of parameters. It can be subject to a lot of attacks and things like that. So it's like they created this idea of the public and private key as, as something that you keep public, something that you keep private. That works out mathematically. They were even using the same ideas of mod, and prime numbers and all that, but it just wasn't like the best. In 1977, as we know, Rivest and the other two created RSA, and RSA basically became more of the standard. RSA is faster. That's one of the things that we will look at today. We'll benchmark a key of the same size for both Diffie-Hellman and RSA, and we should see that generating the RSA key of the same security is 1,000 times faster. So as you can see, that's kind of important, right? So it defeated the technique just 1 year later in both performance. RSA just has, the main issue of breaking it through factorization. Diffie-Hellman has other aspects. Okay, so anyway, historically is an important algorithm to kind of be aware of. And so we're gonna take a look at the algorithm. So basically, I'll just give you the steps. Similar idea, right? And then we'll do a problem basically. Okay, so let's start. Okay, so I'll go over the algorithm first. So Bob and Alice, right? So Bob and Alice are trying to communicate. So we're going to say that Bob and Alice agree on public parameters. Now, these public parameters have to meet certain conditions, right? One of them is a prime number. The other one is a special kind of an integer. So it's actually like 4 parameters that you have to obtain that meet certain conditions within a set of numbers, right? And actually, not all of those combinations work. Some of them are pretty weak, but some of them can be strong enough. So you have to kind of select them really well. But for now, we're going to say Bob and Alice select or agree, select P, which is a prime number, and G. Okay. So these are parameters that they have to agree on, P and G. Okay, but after that they can change them. So that's the first step. So Bob and Alice agree on public parameters P and G. Then Bob and Alice select 2 private values, A and B. So Bob and Alice will select 2 private values. So notice these are private values. So when I say private, they should not disclose them, right? So Bob and Alice select 2 private values. Okay, so we're going to say here, and these are randomly selected, so private values from a group C. Now, C is like, they've established this. We're not going to go into that, but just there's a set of values that you can actually use in this case. All right, so 2 private values, A and B. A and B. Randomly from a group C. From a previously established group C or set C. Okay. All right, so we're going to define these. Go to another page over here. Okay, so we're going to say Bob has A and Alice has B. And then, of course, there's the prime number and also this G number. Okay. So after that, a private value A will have a corresponding public value. So you can see how it's starting to look a lot like RSA. This is kind of like the initial spark, if you will, of the ideas that evolved into RSA. It's actually interesting to note that I was reading that the equivalent of the NSA in the United Kingdom had already discovered this even before them in theory. The same concept, right? Not RSA, but this concept. But it wasn't known because it's a secret agency, right? So they keep everything classified. So that, nice anecdote there. But it was already kind of discovered. Who knows what other governments had already discovered these ideas. But anyway, so they're definitely attributed as the first ones because they had the first public paper. But yeah, several others had looked at this before. All right, so then we're going to say a private value A. So a private value A, right, has a public value. A public value. A value such as, and then I'll give you the formula such as. All right, and so this value will be, so that a private value A has a public value, and I guess I should have said A here. Okay, so equal to, so we have A equal G to the A mod P. So as you can see, it's almost the exact, terms used in RSA. You can see that there's this idea, right? So there's something going on with modulus operations. The one thing that you can conclude, any person, any layman person can conclude there's something going on with modulus operations, prime numbers, certain other numbers that allow you to have this connection between one term and another term that facilitates cryptography. Would you agree? And so this brings up the question, so are these things invented or discovered? Do you know what I mean? What do you guys think? Do you think these things are invented or do you think these things are discovered? Like these algorithms. Who knows, right? It's like the chicken and the egg, maybe, right? So who knows? It's philosophical. I agree. I mean, a lot of people will say this, like, this is nature in a sense. Although we think of physics and chemistry as physical things, we think of this as abstract, but it is in nature somehow. And anyway, something to ponder. So anyway, so that's the idea, right? So a private value A has a public value uppercase A, such as A equals G to the A mod P, right? And you can see these are all the parameters that have been chosen. This is going to depend on whether you're Bob and Alice, so we'll see an example in a second. So now we're going to look at the next step. So I'll create a new slide here. Okay. So then, I guess next step. Bullet. So this value A is sent by Bob to Alice, and A is public. Okay, so that becomes like a public key. So I'll say that. So this value A is sent by Bob to Alice. Sent by Bob to Alice. Okay, so A is public. Say A is public. Okay. Again, one important thing is that prime number. So that prime number is actually the bottleneck. It needs to be a very secure prime number. Okay. So it's really big, like really big. And that's, so that's a problem. All right. So so that I said that the value A is sent by Bob to Alice, and A is public. The next step. The public value associated with B, so B is for the other person. So we're going to say the public. And notice that I'm not really calling these keys yet because they're not the key so far. They're just like stepping stones to arriving at a key. So the public value of B, because remember that each one, Bob and Alice, will have one of these A and B parameters. So the public value of B will be B G to the B mod P, the prime number. Okay, so that's basically how that works. Okay, so we've established that. And then, as just like before, B is sent to the owner of A and is public. Okay, so one new slide here. So B is sent to the owner of A and is public. Okay. So next step. Now, the idea is that Diffie-Hellman works by combining either public value A or B with the other private value. Okay, so that's how it works, and both parties do the same. So I'll write this down. So Diffie-Hellman, abbreviated DH, Diffie-Hellman works by combining either A or B with the other private value. With the other private value. Okay, so that's an important statement there. So Diffie-Hellman works by combining either A or B with the other private value. Such that, okay, and so we'll have A, notice, to the B. You see the combination? So we have the private B and the corresponding A, right? So A or A to the B, which should be G to the A to the B, like that. And so then this becomes G A B in this relationship. And this here is the secret key. So this is the thing that you will use either to derive a new secret key, which you can because you can fit that into some deterministic algorithm, which gives you a value, right? So you can see that. You can even take that, make it a whole bunch of times, hash it, something like that. You have some agreed way, but that's essentially the secret. So here we can see A, B. So I'll redo this in the next slide. Say such that so we'll have A to the B, which is the results in this, G to the A, B, which is going to be G, A, B. And on the other side, let's say one is Bob, one is Alice, you'll have B to the A, and that will give you G to the B to the A, which will be G, G to the B A, which can be arranged to be rewritten as G A B. Do you guys see that? So both of these arrive at the same value, and then this is the way that they achieve. Let me do that in a different color. This is the way that they achieve the secret. Do you see that? This is the key exchange. So remember, what is Diffie-Hellman for? It's not for confidentiality. It's for key exchange, right? It's an asymmetric encryption thing. Only it's not like taking a secret key and encrypting it, right? As we do with RSA, this one has these parameters, and then you arrive at the key. So the resulting value, GAB, is the shared secret key. Okay? So GAB is the shared secret key. So if you notice, this is starting to look a lot like RSA. It achieved the goal of exchanging a key. This is why this paper in 1976, whatever it was, by Diffie and Hellman was so revolutionary, because it's like sparked this idea, sparked almost like a race. It probably then inspired Rivas, Shamir, and Edelman, right, and others to then pursue better approaches. And it just turned out that RSA was better in terms of performance, security, and things like that. Okay, so that's kind of the idea. Yeah. All right, so we're going to look at an example also, right, with numbers in a sec, and then we're going to look at Python, a Python little version of this, and also an OpenSSL. We'll start looking at it as well. So this can be used, yeah, so that's your shared secret key. The downside, I'll just say this part, so make a note of it. So the downside of Diffie-Hellman is that it does not work with just any prime number or base number G. So it's a very particular set that you have to have. You have to do that really, you have to select that really well. All right, so now we're going to look at an example of how this would work, okay? So I'm going to go over here. Oh, yeah, I'm sorry. Yes, so I said the down, exactly. So there's a set of numbers that it will work with. Like, you know, in RSA, some numbers have to be prime, right? They have to be greater than specific phi or something like that, right? So for this to work, there's a certain set of rules. So in this case, this won't work with any prime number. It's got to be like some prime numbers that work, some it's easy to break, right? So that's what that means. So, and as I said, that's why Diffie-Hellman is used. I think I've seen it in applications, but it's not the preferred technique. In fact, there's Diffie-Hellman, I would say, RSA elliptic curves. So if you look at crypto and Bitcoin and all that, a lot of the way that they implement those is through elliptic curve technique or algorithm. Okay? That seems to be the state of the art current. All right. So let's look at an example of how this would work, just kind of with some numbers, but we can visualize it. All right. So I'll use Bob and Alice here, and we should arrive at a secret that is shared. So let's do a problem. Okay. So, step one. So Bob and Alice have to agree on some parameters. So Bob and Alice agree on P equal 23, right? This is a very tiny prime, obviously. It should be massively big, all right? And they also agree on a parameter G equal to 5. Okay. All right, now next step. All right. Alice and Bob will need the secret values A and B that they will select from this set Z, upper, Z or Z. But so I'm just going to say here, Alice will have a secret. This is a secret parameter. And her value will be A equal 4. Okay. So what was nice about this is that it wasn't like, just some stream cipher or some book that you took out a number for that day or something like this was worth, based on some mathematics, you can choose certain numbers. All right. So secret A equal 4. Bob will have a secret also. Which is B equal 3. Let's say that. All right. So this is the starting idea. Okay. All right. Now that we have this, step 3. So I'll try to use all the room I have available here. So step 3. Okay. Now you're going to calculate the parameters. So this is going to be Alice. Right on that. So imagine Alice is in China and Bob is in the United States, right? So they're doing this on their respective sides. So Alice, which has a private secret of A equal 4, wants to calculate the uppercase A, which is going to be public, right? So she's going to do G to her A mod P, right? So then that should give her G is 5, A is 4, mod 23. Do you see that? So there you have it. And so now she calculates A, which is equal to 4, and this is public. That is to say, she can share it with Bob. Okay? So that's the idea. Now, Bob, on his end, or Bob, right? Bob will do the same, needs a public key, B, right? That's going to be G to the B mod P. Okay? So then you do this calculation here. So B be 5 because it's G. To the B was 3. Mod P is 23. Oops. $23. All right. So this should give you a B. You guys know how to do this operation in Python, and you would be able to get something like 10. Okay. So now you have, this is also public, of course. So that's going to be public, right? So you have the private parameters, which give you the public parameters. So now step 5, remember, and one belongs to Bob and the other one belongs to Alice, right? So Bob B, Alice A. So easy to remember, right? So let's go ahead and move to the next page. Okay, so step 5. Right? So now on Alice's side, Alice will do the follow. She wants to calculate the secret, shared key or secret key that they're going to use for encryption. So what does she need? She's going to need Bob's public key. So what is that public? B, right? So she gets B. She has A because it's her private parameter, mod P. Do you guys see that? And then that should give you then, what was B? B was 10. So it is 10. What is A? A should be 4. 10 to the 4 mod. And then prime was 23, right? 23. All right, so this then should give you S equal 18. And you've arrived at the secret, basically. And now on the final step here would be Bob on his side. So Bob is in China somewhere, Japan. Okay, so Bob will receive, so to calculate the same secret, right? Bob is going to receive the public from Alice, A. He's got his B. And then mod P. So this would be for, what was, yeah, Alice is public with 4. B is 3. Mod 23. And that should give you S equal 18. Does that make sense, guys? And that's basically the key exchange. That then they would use that number. Obviously, you'd need it to be bigger and everything, but then they can start, or at least use that in a deterministic algorithm to generate some kind of a secret key. But this is how it would work. And that's it. That's the Diffie-Hellman. This was like the very first publicly paper basically on the ideas of key exchange. And it came around 1976. So pretty important paper there. All right. So we did Diffie-Hellman. Now, a couple of things. The prime number is really big. Needs to be very big. G is an integer that needs to meet certain conditions. Relation to the prime number. Yeah, so let's go with that. All right. So let's switch over to OpenSSL. So we're going to switch over to the virtual machine now and just start looking at some properties of these parameters. So we're going to do the performance test. For Diffie-Hellman and RSA. So anyway, that's it as far as the algorithm, okay? For Diffie-Hellman, as you can see, what are the key nodes? So it's probably not the state-of-the-art in asymmetric encryption. It's one of the first ones, but you can see it already had the ideas necessary to securely exchange a key offline, basically. All right. So I'm going to, hopefully you made your notes there. I'm going to go ahead and stop this screen share, okay? And we're going to switch over to the virtual machine. All right, so now let's share the screen. Okay. I'm going to start my VM. Let's give it a minute. Okay. All right, so let's just kind of, as I said, we're going to do a couple of performance things this week. Today, I'll just do a simple example of a comparison between Diffie-Hellman and RSA, kind of generating the same key that, of the similar size, right? And then after that, we are going to, on Thursday, we'll compare symmetric encryption to RSA, also to kind of address performance. All right, so let's go ahead and here, ls-l, let's go to the desktop. Here. Oh, do you have a question? No, just stretching. All right, so it's all right. CD ITLs 350. Oh, 2024. So I'm going to do a new folder. I'm going to call this one Diffie-Hellman. Okay, clear. LS. Well, all right, here we are. So the first thing is you just, go back to OpenSSL for a little bit. So OpenSSL, we've done the other day, I think last week, I was doing some examples of generating RSA keys with OpenSSL, if you remember. I think I tried generating one that was 31 bits long and it didn't work. I think 256 was the smallest I could generate. So you guys kind of know how to do that. So OpenSSL, if you want to generate a parameter with Diffie-Hellman like a key, you do DH param. That's Diffie-Hellman. Okay. And then we can specify probably the size 248, 2048, and there it goes. It's going to take a long time. Do you see that? Right. So, but there it is. So not that long. But it took a little bit, right? So that's what this is addressing, right? The idea that these algorithms can be slow in the generations because they have to try a lot of things. We're not going to get into all the specs of like implementing this in Python fully. So I just wanted to give, because it's not really one of the algorithms that's the most important. But I wanted to, show you guys. So you can see the parameter there. If you guys want to benchmark something, I'll show you how we can do that in a simple way. Just for contrast, though, so I did that, OpenSSL DH param of a specific size. We did this already for RSA, if you remember, OpenSSL gen RSA, and then 32 I tried the other day, and that was too small, if you remember. So in this case, I can try 2048, should be about similar key size. This is just a key, right? So we're just thinking of one key or the other that we can use, and how long it took. Did you see that it was faster, right? All right, so let's take a look now at a benchmark that we can do. So I'm going to try to benchmark these two keys that are generated with this initial input of 2048 bits. So I'm going to do time, and there's several ways of doing this. We're going to look at this on Thursday. There's a speed test that you can do, another speed test for all the algorithms. And then we're kind of going to do one manually, which basically we're just going to encrypt something for like 10,000 times, right? And then obviously you can take the time that way. But obviously we can try something like this. So let's go ahead. So I'm just going to add the word time in front of it. OpenSSL DH param 2048. Oops, 2048. Notice it says 2048 long safe prime. Do you see that safe prime? That means that you can have primes that are not safe, right? And that's what I was saying. So you have to really specifically pick that. So got some statistics there. Real user and system. All right. So now let's run this again. So it would be OpenSSL, time OpenSSL, gen RSA, 2048. Okay. So how can I... All right, there is no, okay, so you guys, so Diffie-Hellman, 18.6.9, RSA 0, 0, 0. Do you guys see that? So you notice that RSA was faster, correct? Statistically at the time. Yeah. So that's it. So this shows you, you know, obviously when you're building something, immediately you're going to gravitate to the slower one. Are they both equally secure? Maybe, but this one's faster. They have different types of attacks. Did somebody not select the prime correctly, etc.? So at the end of the day, RSA seems to have won. And then there's elliptic curves, which seem to be even slightly more secure nowadays. Any questions? Yeah, please, sir. Yeah, sure. So I just added the word time in front. So time OpenSSL Gen RSA 2048, that's for the RSA algorithm. And then time OpenSSL DH param 2048 for the Diffie-Hellman. And then this allows you to benchmark them basically and get an idea. All right, so as it turns out, so if you want to put things in scheme of things, Diffie-Hellman way slower by 1,000 is the factor, is my understanding. And it seems to be correct, given that this is almost 0.20 versus 18.55, right? So my understanding is a factor of 1,000. And then, so Diffie-Hellman, the slowest. Then we have RSA, which is slow, but we only use it for keys, not for encrypting the whole movie. And then something like AES, fast, because it's XOR operation, and that's done at the bit level, right? So that's meant to be pretty fast. Remember, you may see code, but at the implementation, the underlying C code is at the bit level. So it's really fast.
Is there any real reason to use Diffie-Hellman, like any practical reason?
I don't know that anyone would use it. I'm sure some applications are there that is like, oh, this is a Diffie-Hellman secure one because it's got the secure primes. OpenSSL has it. So it's there, and it says it's a secure prime. You see that?
Yeah.
So 24-bit long modulus. Oh, sorry, no. The 24-bit long safe prime. So it's probably secure, yeah, but it's slower. Most people will use RSA. And then really, as I said, Diffie-Hellman was the originator. I think RSA won the battle, and nowadays elliptic curves are what is implemented in cryptocurrency. Any questions? All right, so now that we've done that, you know, the fun exercise might be to just try this out in Python, right? So you guys probably could do this on your own, but let's kind of try it out and see. So we're going to do the example that I did by hand, and we're just going to implement it in Python and see what happens, right? So we should know the operations. All right, so let's go ahead and clear here. Are there any questions, by the way? Of anything? All right, so let's go ahead. So we are in the folder. So I'm in ITS 350 and Diffie-Hellman folder. So here's a perfect place to create our script. So I'm going to do Diffie-Hellman example.py. All right, so we will define some parameters here. So we'll need to have our P, our G, an A, and our B. So obviously, I'm not going to have functions for selecting those, as that can be somewhat challenging. But we're just going to see the relationships. So let's define the parameters here. Remember, there's Bob and Alice. We need a P, 23. We need a G, which is 5. We need an A, which is 4. We need a B, which is 3, right? So that's just the example I did. Then we want A here, and we set that G to the A mod P, right? So that should be, I guess we can hard code it. No need to create functions. So A, what is that? G to the A, right? Mod, and then here, just 4. Parentheses. Mod was the same mod, percentage. P is 23. Oh, P. Okay. And that would give us, we can print A, right? Then we can proceed, calculate B. Which will be G to the B mod P print B. Okay. And then I'm going to say Alice. So S for Alice, Alice actually, would be B to the A mod P print S underscore Alice. Okay. Bob. So this would be S Bob should be A to the B mod P, right? And then we print S Bob. It should be S Bob. Okay. So let's go ahead and try this out. Python 3. What do you guys think? It works, right? So it meets the condition. Keep in mind, though, these are parameters that were selected that meet the conditions. You'd have to have functions that generates all these parameters. It may not work for just any kind of number, just specific ones. But this is as far as we're going to take this. Diffie-Hellman just for kind of historical reasons. So you know now of another algorithm that helps you with the key exchange problem. The significance, as I said, is kind of the first paper on this that kind of started the whole idea of asymmetric encryption, and they coined the term public and private. Any questions? Does Diffie-Hellman make sense, guys? Yeah? All right, that's it as far as this algorithm. So I'm going to move on to a new topic, all right, which is not a new topic, but the same topic of digital signatures, basically. So we're going to go back to that. I do have some slides, so I think we have some time, like 40 minutes or so we can just look at the slides and kind of summarize all the material. And then I guess I won't get into the lab today until Thursday and stuff. Right? This is Diffie-Hellman. Right. So yeah, so I finished this. So I almost kind of want to end this video because they're separate things. So I'm gonna